Up to volume.
What?
You on? Audio? Yeah. Okay, fine.
Okay, so we start the recording, yes. So it's a pleasure today to have as our speaker Professor Markus Bruggen from the University of Hamburg, who's visiting a full week because he's one of the winner of the visiting fellowship from the Physics and Astronomy Department of the university. So Markus graduated and got the PhD in Cambridge in '99, and he was doing that working on solar physics. Then he got a few postdocs, both in Cambridge and in Max Planck in Garching, and he switched gradually to cluster of galaxies. Were one of the first people ever doing simulation of feedback and cavities in cluster of galaxies. Then in 2001, he moved to Jacobs University Bremen, Germany, as a professor. He also became one of the PI in the builder list of LOFAR. As a personal note, in 2010, he was so inspired to hire two young postdocs from Italy solving Mayan and Annalisa's two-body problem. Then in 2012, he became full professor at the University of Hamburg. And over years, he became also involved in Rosetta, ASCAP, several instruments. And now he's also the responsible of gravitational wave detection for the Excellence Initiative in Germany. And today he's going to tell us about the radio magnetic aspect of his work, I guess. So please, stage yours.
Thank you. Great to be back in Bologna. I brought the weather with me. I've noticed.
Too dark.
Okay. Interesting. In Italy, I get rain warnings on my phone, even if the slightest of drizzle. Anyway, good, many familiar faces in the audience. I'm going to talk about a few things that are hopefully connected in some ways, and start with maybe showing you what I think is one of the surprising, or at least to me surprising, advances in the last 2 or 3 years in radio astronomy. You know that radio astronomers have been developing ever better instruments, especially going to lower frequencies, going to higher spatial resolution. And one of the things that has really emerged is that you now look very closely to things in the radio. The radio synchrotron emission, what you see is...
Sorry.
You want to give my talk?
No, I wanted to kill that button. Sorry. My bad. Where is that button? I wanted to kill that. Sorry. Oh. Go ahead. I don't know.
Yeah, I don't know. Anyway,
sorry.
Maybe we'll work without it. Anyway, now what we see is here are various images and various bits in the sky. You see here, for example,
Yeah. No. We tried already.
I don't. So there.
I think it's okay.
Escape, click here, and full screen again.
Okay. Sorry.
Is it still okay online for the online people? Or?
Yes.
Anyways, good.
It's okay.
Thank you. So if you now look at radio continuum images in the sky, whether this is the center of the galaxy or this is the center of the Milky Way, in the L bands, so you see all these different filaments here, very thin. I think sometimes some people call them harps, like the string of a harp. And here in the galactic center, then in galaxy groups, Marisa here found this really weird source. Somebody I think called it the lady in the hat. I'm not sure whether that's still the official name. It's a really strange radio source that you see here. Thin radio bits and pieces in galaxy clusters. People have seen this. Radio galaxies used to look very different. Now, if you look at the radio galaxy, if you look at the recent pictures, they often look like this. They're very filamentary. Radio relics, they used to be known as these arc-shaped sources. They're essentially radio shocks. So these are just like in supernova remnants where you've got a shock wave, just like an arc that shines in the radio. Now, if you look very closely, it's all very filamentary as well. And there's another radio relic as well, all that done here. So this is work by Kamlesh. This is a galaxy cluster with this name, about 2256. You see, this is a galaxy cluster, but in the radio, you see these red images here. They're very large. You can see here, this is 500 kiloparsecs. And now Kamlesh has found that if you look very closely, very high resolution, you can see that this filament, that this relic consists of hundreds of filaments. Yeah. So this is all new, and I don't think we fully understand why this is. Now, a student of mine, together with Franco, has actually worked on an algorithm to extract all these filaments from structures like this. You can do this by using various clever algorithms, and you can extract these substructures and do some physics with them. But I'm not going to talk much about this. This is a paper that was just published last week. This is the center of the Perseus cluster seen in LOFA, LBA, HBA. So this is a 140 megahertz image of the central part of the Perseus cluster, NGC 1275. It's the name of what you, this cluster has been known to host a mini halo, so a diffuse radio source at the center. Now we know it actually contains a radio halo. Plus, if you look at this, it's got all this mess in there. And if you show this to people who do models, who do computer simulation of this, they say, God, what are we going to do with this? There's all these radial filaments here that you see again. There are azimuthal filaments here and edges that you see, all kinds of bits and pieces. There are extensions, arcs, and all kinds of things that you see here. So I think this is now generally true, that if you go and look now at these at these radio structures, they now look all very, very different. This is the source I mentioned that Marisa worked on. This is a Nature Astronomy paper. This is this source in the galaxy group. It's very obscure, and almost nobody knew this source. It's a group, and this has appeared to, so the center of the group is somewhere here. There's a radio jet here, and it's got this strange source. This is again LOFA image in 144 megahertz. Now this is the LBA image, so even lower frequencies in LOFA. And you see that there's an active jet in here, and this is stuff that must have come from an older episode of radio, of whatever this AGN has produced. Yeah, probably underdense bubbles of hot gas. They rise up, and then they usually produce some cavities or lobes, or maybe they look a little bit like a cap, like buoyant bubbles, but this doesn't look anything like it. This looks really, really weird. Also, this emission here, as you can see here, if you go to low frequencies, they become brighter. So this has got this steep spectrum. So this means that the electrons that produce this emission are fairly old in here. And if you look at the time scales for this, is usually these electrons should have already faded. The emission should have already gone away. It hasn't. Still there. The morphology is these thin, wiry structures. So somehow magnetic tension, somehow magnetic fields need to be involved in order to produce structures like this. At least that's the prejudice that people have. Other sources as well. This source here. This radio galaxy, it's got a tail, it's got all sorts of filamentary bits in the lobes as well. Almost everything. I could go on now. I could fill now the whole hour by just looking at this. This is a galaxy cluster with a very powerful radio source in here. It's got 3C40A and B. There's two radio sources in there. There's again, this is a radio galaxy, so the supermassive black hole sits in here. There's an overlay of the optical, so these are the optical galaxies. The orange is the radio image. This is the radio image of the meerkat. So this is an Australian instrument, and radio interferometer in Australia. That's eventually going to become part of the SKA. And this is the angular resolution that you see here. And again, so you've got the supermassive black hole somewhere in the center of this galaxy here. There's two jets that inflate these lobes, and then you see all this sort of stuff here. And it has a lot of fine structure in here. There's connections maybe in here. And what's somewhat striking is that somehow it seems to push against something, and you see these filaments here. They go on for about, so this is 100 kiloparsec here, nearly 200 kiloparsecs all the way to the east. So these eastern filaments, they stay parallel, fairly collimated in here. This is really weird. If you look at this a little bit more closely, you can measure what the width is. They're only 3 to 8 kiloparsecs across, 200 kiloparsecs long. Now, at the location where you see these filaments, the X-ray surface brightness goes down by about 20%. So it feels like these are empty tunnels into which electrons are being fed in, and then they somehow almost instantaneously, without aging, there are no gradients in spectral index that would tell you that the electrons lose energy or cool by losing the energy as they go along in here. So it's a tunnel, and this tunnel is threaded by magnetic fields, because this is the radio polarization that you see here. So the black lines give you the direction of the magnetic fields that you infer from the radio data in here, and you can see that it pretty much follows these tubes. So these are flux tubes filled with relativistic electrons that emit synchrotron emission, and that somehow have carved a tunnel into the X-ray emitting intracluster medium in this Galactic cluster 194, where this is. The degree of polarization is very high. It's 50% polarized. This is very, very high. So yes, you can do all kind of things, and Larry Rudnick and several others and myself wrote a paper on this a couple years ago. So this goes on and on and on. So this is also a famous source, a famous galaxy, one of the first images that Meerkat released. And again, you see that all these radio galaxies are surrounded by magnetically dominated structures that really thread everything, govern the motion, at least of the relativistic electrons, and maybe of the thermal electrons as well. So what you see, all this filamentary stuff, is the result of the magnetic fields that are produced by turbulence in the medium in which these radio galaxies sit. This has been predicted by simulations. This is a very recent simulation of supersonic turbulence in magnetohydrodynamics, very high Reynolds numbers. And so this is the whole medium in which these galaxies sit. It's believed to be turbulent. It's believed the turbulence is supposed to be supersonic, faster than the speed of sound, which then gives the scale to the turbulence. Usually turbulence doesn't have a scale. Turbulence, if you're supersonic, you get a sonic scale in there, and the shape of the turbulence becomes like this. It becomes intermittent, meaning you get these long, stringy, looks long and stringy, that's where all these shock waves intersect and produce this kind of morphology.
But that's supersonic.
This is supersonic.
But in the intercluster medium, you expect such a supersonic.
Most of these galaxies do not sit in galactic clusters, but yeah, it's not clear whether this is in the center of clusters supersonic. So what I'm trying to say is that these filaments, what you see in there is the underlying structure of magnetic fields that's being fed electrons to make them shine, to tell them what they look like. That's probably what it looks like. And also, of course, our local god of MHD turbulence has done this as well, and he did the first Frankie did the first high Reynolds number simulation of galaxy clusters and produced beautiful images like this to look at where the magnetic fields come from, how the turbulence amplifies the magnetic field in a dynamo. Right. So I think the point I'm trying to make by way of introduction is that extragalactic space is probably threaded by magnetic fields. This has been expected from simulations such as these ones. And these are intermittent magnetic fields that have this funny structure. And now I think we're beginning to see this because the radio galaxies, they give us access to look at these fields and see what these fields look like. And there's a lot of unsolved problems. For example, why these electrons live so long in these filaments and all kinds of things. Anyway, let's go and try and simulate this. Let's go and simulate magnetic fields and radio galaxies in this. And so we produced a simulation that looks a bit like this of an AGN in a cluster. So the cluster is a static cluster. It's a bit like a Perseus cluster. So it's a cool core cluster. And we put a black hole in here, and this jet is self-regulated, so you can measure the accretion rate onto the central bit where the black hole is supposed to sit. And then there's a prescription how to power a jet. This jet is magnetized, and the whole medium is magnetized. There's a turbulent magnetic field in the ambient medium. We talk about the details later. This is a simulation of very high resolution. It's 24 parsec is the resolution. This is only the inner bit of the entire simulation, which is the whole volume is much bigger. The axes here are kiloparsecs. See here in here. So the jet is about a bit more than 100 kiloparsecs all in length. Bear that in mind for what I'm going to say a little bit later. If you're interested in numerics, the code that we use is Athena PK. Athena is a code, a hydrocode, and PK stands for libraries that make this run on GPUs. So this is a run that runs on many GPUs, tens of thousands of GPUs, and it's very fast. This is work, by the way, it's led by a student of mine, Martin Fournier, in Hamburg. So this is a cluster. And what we wanted to see, this intercluster medium is cooling, by the way. And what we wanted to study? We wanted to study how the jet and what you observe in the center is affected by the magnetic field and by the cooling. We've got cooling in here. This cooling causes thermal instabilities, and these thermal instabilities make the gas condense out. This condensation is being offset by the heating that's being put in by the jet at the center. I wanted to see what happens if you go and do this in a realistic way. This is what you would see at a certain point. The time is not actually very relevant. This is the inner part of it. It's 5 kiloparsecs here. And you see the cold gas in here in this bluish bits. And you see the hot gas as this orange haze up here. And you can go and work out what this would look like in the X-rays, in H alpha, and bits like this. So this is what this looks like if you have a jet sitting in a cluster. The gas cools down and falls down onto the black hole in these long stringy filaments that go up. They fall into the central region, then they feed the black hole, and the black hole puts out the jet. And that goes out here, and these filaments sit at an angle. So the accretion goes up as an angle to what these jets, to where these jets propagate out here. Here you can see, first of all, the center of the Perseus cluster. This is the H alpha image of the center of the Perseus cluster here, and you see 1275 in here. And this is our simulation here, the simulated H alpha emission that you get. Difficult to make a one-to-one comparison, but it looks though that is the size ranges, the thickness, and the length of the emission that you would get seems to fit. Now, if we did the same run without magnetic fields, what happens if you switch those off. And what you then get is this. It looks very, very different. So it's important that magnetic fields, the strength is actually not that important, but magnetic fields ensure that you, well, are essential in order to reproduce the morphology of the cold gas. And by reproducing the morphology in this cold cluster, this also means that they govern the accretion onto the central black hole. And the entire feedback cycle is also governed by the magnetic fields. So magnetic fields are initially turbulent, that they are so that, yeah, I'll come to what the magnetic fields inside these filaments look like in here. So these filaments now we can cut out the filament I showed you. So we cut them out and put them all on this axis. So this is actually only one particular filament that we go and traced for a certain time. What you see here in these panels is the gas density, the temperature, the radial velocity, and beta. Beta is the ratio between the thermal pressure and the magnetic pressure. Meaning if you have a low beta, you have a high magnetic field. Okay, so what you see here is that these filaments over time sort of get stretched out and at some point become smaller again. As you can see this, so these filaments are of course cold. You can see here they're blue, but this filament is so this cold gas, this cold atomic gas that's being pulled up by the jet. Yeah, you see here the radial velocity. Now, positive radial velocity means they're moving outwards, and red means that it's folding inwards. And you can see here that these filaments are being pulled up. Now, imagine you've got this AGN. It produces hot gas that rises buoyantly in this just atmosphere, and as it does so, it just pulls up, just like paper clips in the magnet, pulls up these filaments and they go back upwards. Although at some point they fall back in as well, and always there's parts that fall back in and feed the black hole. So these filaments contain gas that's both being pulled out and also gas that falls back in. Right, and this happens along this very stringy morphology. And the reason for this is sometimes a little hard to see that the magnetic fields are aligned with these filaments. You can see them here. They were all messy before, but the gas cools, the magnetic field gets compressed just by flux conservation inside these filaments, and then they're pulled out, and that means the magnetic field lines radially in these filaments. Anyway, there's much. Yes, go on.
And in this kind of simulation, do you have a treatment of thermal conduction, both in the presence and the absence of the magnetic field?
There's no thermal conduction. No, thermal conduction is another Pandora's box that you open because nobody knows what how much conduction there ought to be. It's essentially a free parameter.
The difference between with and without magnetic fields is nothing.
It's nothing to do with conduction. No, yeah. So conduction would have to be anisotropic conduction. I think if you wanted to put in conduction, so that means conduction only, heat conduction only along magnetic field lines. And then you would have to put in diffusivities, and nobody knows what they really are.
But if that's a topology, you wouldn't do much because the magnetic field is aligned with the filament. So you don't have conduction between cold and hot because you need to go perpendicular to the magnetic field.
Yes, the magnetic fields would probably shield and protect these filaments. That's generally true actually also without thermal conduction. These filaments, they live for very long times, right? And even though they're very thin. And the reason, and they move at fairly, they go up to sometimes few hundreds kilometers a second. The reason that they survive at all is that the magnetic field stretch them, so they're not being disrupted by shear motions and things like this. So yes, the magnetic field has various functions. You see this here. This is now better to see how what this looks like. You see here in this filament, beta, this value is fairly low, meaning the magnetic field pressure dominates in here. So these filaments are magnetically dominated. They are thin and they're threaded by magnetic fields. That is almost parallel, but it's not perfectly parallel. So depending on how much heat conduction you have, you know, all sorts of things could happen. And this is true for all the filaments that we observe. And we can then do, we can look at the life cycle of these filaments. So this is for different filaments. We can just pick one. Let's pick this one here. So these are, so what we plot here is first of all, the velocity, the radial velocity only with respect to the cluster center. Now, the color is the age of the filament. So the filaments start, this is a filament that starts going outwards. So it's being lifted up buoyantly, fairly low velocities by the rising bubbles that are inflated. And then they start to fall down as they start to fall. So this is the time they do up here, this particular time up to 160 mega years. And then they fall down back onto the center of the cluster. You see here. And here on the y-axis, you see the mass in cold gas, the total cold gas mass inside the filaments. And you see they're being dragged up. And as they're being dragged up, there's more condensation. So there's actually, you pull them up and more gas cools onto, from the hot medium, cools onto these filaments. So they grow in mass and they keep growing even as they fall down. At some point, they fall down with such high speeds, about 200 kilometers per second, and then they start to lose mass as well. Okay. And you see that this sort of life cycle is, we see this more or less, right, for all the filaments.
So the velocity doesn't change time. How you see expansion and falling back?
They are all made, so they're initially they're being dragged up. Eventually they fall down.
Branch of the gray branch of the.
Yeah. So most of them fall back. So this is
Okay.
the center of mass.
Most of the diagram, the sky
Yeah.
is falling back.
That's right. So this means also that so there's a bit of a chicken and egg problem here, where the gas condenses and then it's being pulled up, or whether the gas condenses on it all the time. And this means that they're being, in the entire stage, they start to condense gas on them by thermal instability, and they lose mass by shear instabilities. There is a constant battle between these two things. And magnetic field, without magnetic fields, you get completely different results. Okay.
What do you mean for cold gas here? Because in the previous map, the temperature was about 10⁶ Kelvin.
Ah, right.
And
So we cool down all the way to 10⁴ Kelvin.
okay.
And what we call cold gas, so the temperature here, we call cold gas everything below 10⁶ Kelvin.
So those filaments, there are actually cold gas.
Yeah.
Because it looks like 10⁶, but there is
Yeah,
also-
yeah. So we cool all down to 10⁴ Kelvin, which is the peak of the cooling
And
curve.
in the velocity maps, or plots that you just showed, you never reach the free falling velocity. So they are
Not quite, no, not quite. Yeah. It's probably the tension that prevents that. Yeah, it's not quite free falling. Yeah, I've noticed that too. Good. I think I should speed up a little bit. People who are interested in this sort of thing, there's an ongoing debate about the clump statistics. So in thermal instabilities, say you have a little bit of gas, you let it cool. At the end, what kind of clumps distribution do you have? Yeah. How much mass is in? Yeah, how many clumps do you get of what mass? So this is mass, 10⁹ solar masses to 10⁴ solar masses. How much is there? There's people at power laws, and there's people who do different things. People who are star formation are interested in this sort of thing. Anyway, there's an ongoing debate about this. This is actually hard, but I won't get into this. Now, I want to talk about the second bit of my talk, and this is about other radio galaxies, the extreme end of radio galaxies. Now let's go back one bit. If you, the largest angular size radio galaxy that you see, you had radio eyes, you looked up in the sky, would be Centaurus A, because it's very close. Now this is what it would look like in the sky. It would span 10 degrees. And it's only 600 kiloparsecs long only. It's a large radio galaxy. It's very, very big. And here, so this is one example of a huge radio galaxy. It's also nearby. So this is 20 full moons all across this radio galaxy. Amazing how big these objects are on the sky. And people have been interested in giant radio galaxies for a while. Giant radio, there's various definitions what you call a giant radio galaxy. Many people say it's more than, I mean, this is totally made up. Radio galaxies have more than 700 kiloparsecs. I think that's what I'm going to use from now on. There's some other papers who say everything has more than 1 megaparsec. Yeah. Anyway, so these are huge radio galaxies. This is one of the record holders up until very recently by Martijn A in Leiden in here. It's a radio galaxy that's 5 megaparsecs across. So prior to 2022, less than 1,000 of these radio galaxies were known, of these giants with this definition. And now with LOFAR, so these things are difficult to see because they are extended on the sky, they've got low surface darkness, very difficult to see, very difficult to find, impossible to find automatically up to this day. But now we've got more than 10,000 of these. And now you can look at these radio galaxies. You wonder, why would you look at this? Aren't they just big? Well, they're interesting because that means the radio jets must be on for billions of years in order to produce them, because it takes 1 to 2 billion years to inflate such structures on these sizes. Yeah, the heads that if you assume, just assume that the head of the jet propagates 1% of the speed of light, and you see how long do you need in order to cross 3 megaparsecs, and that gives you billion years in here. In those billion years, not much is allowed to happen. No winds, no big bulk motions. This galaxy is not supposed to move much in here. They still stay pretty much on the line in here. Even though the black hole, in order to power these things, the black hole needs to double its mass. In order to power these sources for this time, you need to accrete about 1 billion solar masses. Now, if you accrete masses of this size, usually you create havoc. The whole mediums, there's mergers and things. Can't be too bad because this thing still stays in place in here. So, yeah. So, question is, so do they? So this is something I found on CNN and some of the press releases that the Leiden people did in that time, where I published this paper for Theorem, one of the other big sources in here. So one of the ideas is that these giants sit somewhere, maybe in filaments, or and then these jets pierce the filament, and just expand to these voids. This is the case that they may all then they're interesting because then they fill the void with all that radioplasma and negative waves that comes along with it, and then this fills the voids and magnetizes the whole universe. This is supposed to be actually a movie. Doesn't play. It does. So this is also I also stole this from CNN. They made this. Not sure who made this. Anyways, the first GRG was discovered actually already quite some time ago. It was then already a huge size, with the Hubble constant being different now. It's only slightly less than 5 megaparsec, and then for a long time people didn't really find many of them. Yeah. GRGs, as these giant radio galaxies are related, are not the most radioluminous sources, but they've got the lowest minimum energy densities because they are so huge, and very low surface brightness as well. But they've got the highest energy content. So if you sum it all up, what are these giants here? This is a now recent discovery in in lots in the LOFAR survey. This is what they look like. Look through the data and see what they look like. Now the challenge is then, of course, to find the host. And then there's people first thought this was the host, and then now people see that this is the host, depending on this requires a lot of looking and pooling of the data. This is the specialty of Heinz Andermach, who I work with on this topic. And yet, once you've got the host, you have to get the redshift, and then once you've got the redshift, you can work out what the total size is, and then you can work out, is this a giant radio galaxy or is it not a giant radio galaxy? And people have looked at these now. There's various samples, heavily biased to the north for a long time. Now with all the southern hemisphere radio telescopes coming online, this is changing, and now we find a lot of giant radio galaxies in the southern skies in here. This is still back from the to the northern sky. This is work by a former PhD student of mine, Marco Simonte, also from Bologna, of course, who is coming here, and he found in the LOFAR deep field. So LOFAR did produce some deep images by looking at certain parts of the sky for 50 hours or more. And then he found just single-handedly 280 giant radio galaxies. This gives you a typical, you can work out what the typical density on the sky. So there's about 3 giant radio galaxies per square degrees. That seems to be the number that you have. Now, to the question is, do they live mostly in underdense regions, in order to explain why the jets can go so far without problems? You can now try to work out what is the density of galaxies per megaparsec square on the sky. And you can do this for giants, which are the blue ones, or you can do this for normal radio galaxies. And you can see there's not much difference, except for at the very dense regions, it seems to be that there are fewer giants. But anyway, statistics isn't that great. It's not quite obvious. What is clear is that giant radio galaxies are still fairly rare. So this is the new work, which is unpublished, where we just found, we thought we'd go to the very extreme end. This is supposed to be 3 megaparsecs. So now we found a sample of 110 giant radio galaxies that are more than 3 megaparsecs long. And here is a histogram of all the giant radio galaxies that are known. Everything that are known so far, and the blue ones is our sample. And you see here that the slope steepens quite a lot at these large sizes. So that means very, very large radio galaxies are rare. So I'm really looking at the rarest objects in the rarest radio galaxies that we find. Still 110, so we can do some science with it. These radio galaxies we found mostly in published LOFAR data, some in LOFAR deep fields in here, but also in other sources. So NVSS, ASCAP, MWA, and other sources in here. So there's 110 of these. And out of those 110 more than 3 megaparsec, these 5 are larger than 5 megaparsecs. That's what they look like. And so these are the hosts in here, within these magenta crosses, and you see here these giant radio galaxies. Now, what is striking is this is 5 megaparsecs every single time, sometimes even a bit bigger, and they're very straight. So you can go and measure the bending angle, meaning how much do they deviate from a straight line. And you can plot their bending angle here in degrees as a function of their size. And yet, this is the one that was previously the record holder. Just I think last year. Now we have all these sources in here. The statistics isn't all that convincing, but yeah, you may think that with largest linear sizes, the bending angle becomes quite small. These are small angles, so the median bending angle here is something like 3 degrees. Now 3 degrees to get 3 degree bending angle on a 5 megaparsec source means that the source can't have, the center can't have moved with respect to the head of the galaxy by more than 100 kiloparsecs roughly. Yeah. So 100 kiloparsecs over 2 gigayears, 2 gigayears to produce the sources, means the velocity, the velocity that this source suffers must be really, really small. Yeah, less than 100 kilometers per second. Nothing must happen to this environment, either to the lobes nor the host galaxy, over 2 gigayears. I find it really, really hard to believe how this works. I know Franco has some alternative theories now on how this works. He might talk about it in his own time. Anyway, this is really odd. You can look at their powers. Not that interesting. I can talk about radio galaxy evolution. None of this really makes sense in terms of normal models of galaxy evolution. And you can see maybe the reason why I just want to point out that some of these really big ones have extreme powers. But the ones that are more than the five ones I showed you before, more than 5 megaparsec, their powers isn't actually extraordinary. What extraordinary is really the consistency with which they have been on, this black hole has been on.
Normally you would expect to see a correlation, I guess. I mean, in a naive way, like more power to make a larger source. Or...
Yeah, that's not true. Anyway, well, there's a lot of uncertainty actually how you calculate this. Yeah, anyway. There are other puzzles, meaning if you go to high redshifts, now we also have quite a few at high redshift. This is other one of our proposals. You would think that the GRGs somehow go down because of the inverse Compton cooling, which goes like 1 + z to the 4th, you would get surface brightness dimming that should kill these sources. Okay. Some of these GRGs we have at fairly high redshifts. Also doesn't seem to be the case. Another weird thing. All right, so let me go and let you not give you many answers, but maybe I piqued your interest. First of all, what I want you to take away is everything is filamentary. Yeah, if you now look with the sharp eyes of new radio telescopes, everything is filamentary. And I think that this is evidence for magnetically dominated structures, where magnetic fields are dynamically important. And maybe this is because of turbulence that produces long-lived filamentary flux tubes that are somehow filled with cosmic rays, and these cosmic rays are somehow also kept alive in some mysterious fashion. Then in galaxy clusters, there's multi-phase gas because of cooling. We see this in multi-wavelength observations of galaxy clusters. This is clear. Now I think you can reproduce this using simulations that both include AGN feedback as well as radiative cooling, as well as magnetic fields. All that is important in order to explain the interplay between the thermal instability and magnetic fields, as well as the AGN. Okay, that's all connected to magnetic fields. Then the giants, for the giant radio galaxies, I think this is a rapidly expanding field with a lot of interesting things. You can also do cosmology with these giants. You can do all kinds of things. You can now find them just in the low deep field, which is a tiny fraction of the sky. We found 280 of these in here. And one thing that I actually didn't mention is you would think that because these giants, they move out, they're so large, they seem to be so undisturbed, that they live in these underdense regions. Now I've given you a little bit of evidence that this may be the case. But our sample of 110 giants that are larger than 3 megaparsecs, out of those, so we cross-checked them with cluster catalogs, nearly 20% living clusters are actually the brightest cluster galaxies. So they actually managed to get out of the cluster. Now the cluster, in 2 gigayears, the cluster must have grown, probably doubled in mass. And they belong to the cluster and stayed straight and so big. I don't know how this can work. And they sit there, so they are also the brightest cluster galaxy. They're just not sitting in the cluster, they're the bright, so they sit probably at the bottom of the potential well. So maybe the bottom, so the center, the anchor of the giants, maybe that sits still because it's the bottom of the gravitational well, and the mergers that this cluster suffers aren't too dramatic. But then usually the ICM gets tossed about a lot. So that doesn't seem to be the case. So this is another thing I find quite interesting. So 20% are in clusters. Lots of them with diffuse sources. So this is the big sample, and people have been showing various record holders now. This is now really an impressive sample of huge proportions, where you can see even 5 GeoGs with sizes larger than 5 megaparsecs. And there's a lot of things that you can do with this, starting from radio galaxy evolution to cosmic magnetization. Maybe just stop here, so Frank, we can go.
And you are the chair.
You're in charge.
Thank you. So I was wondering, since you characterize this giant radio machine, so you've been looking at those fantastic images. So how much the size of those jets are well understood? So considering the fact that the universe is in 3D. So you're talking about 5 megaparsec, you're talking about 7 kiloparsec, but these statistics should suffer about the projection effect, but also the calculation of the bending should suffer a bit.
Yeah.
So how well are those understood?
Yes, not very well. So there's been some attempt by the Leiden group to attempt some kind of reprojection of these. So good that you mentioned this. Everything I've mentioned was projected size on this line. So this means they're actually bigger. They're actually quite a bit, they can be quite a bit bigger. So if you try to model this, so if you want to model this, you need to know what's the underlying real distribution. So people have tried to model them as Pareto distributions. These are fancy power laws essentially, and then you can do this, and then you can work out each reprojection formula to make them bigger. So I definitely did not want to do this because it depends on that assumption, which is not really justified. But yeah, you can try and do this. But yeah, it's a good point that this is projected, and the actual size, of course, even not.
I was interested, I was curious about the initial conditions of the simulations that you showed towards the beginning. So how are they calculated? Are they cosmological? And if so, what does t equal to 0 represent?
No, so this is a static cluster in hydrostatic equilibrium that's been running for a billion years, and it sits there, it starts to cool. As soon as it starts to cool, the AGA goes off, and we go and watch it settle into some sort of steady state. There's no cosmology in it, meaning there's no big bulk motions, there's no mergers, there's no substructure in it as well, which teach things. The point of the study was just to look at the interplay between the thermal instability and the magnetic fields, without the other mess that comes about by being a real cluster in the real universe.
Very interesting. A question about the cold filaments. If they are magnetically dominated, they should have a density much lower than expected from thermal pressure. And I don't know if this is the case. I mean, the few examples that I have in mind have a density which is probably something like a factor of 2 less than expected, so not a lot. So I wonder if there are other measurement that you can do, I mean, to prove the magnetic field or something like that.
Yeah, so that's a good point. So we looked at this, and it turns out that, so we haven't done proper comparison of that with observations of what they are, but what we found is that these filaments are slightly overpressured, and they still don't expand much because they get condensation onto them, which they have a condensive flux, which provides an additional source of pressure, around pressure, to keep them in check. Plus there's magnetic head tension that helps that. So yeah, so I think, yeah, I'm not sure how far away we are. Can't give you a definite answer, but I don't think this would be very accurate. Yeah. Yes.
Okay, so if you have a GeoG in a cluster for 2 gigayears, this cluster doesn't undergo major mergers, so it's probably a cool core, so it's cooling, but there is no mechanical feedback for 2 gigahertz because you need bubbles there. Instead, you have a super thin jet going out. So this is another
Yeah, so we
question
don't know
on how
much
that
about
cluster
it.
can.
So we don't know much about this cluster because we got these by cross matching with these Wayne and Ham cluster catalog, which has these several thousand or no, I think really clusters that have something like this, something ridiculous number. So these optically reflected clusters, and we also cut them off with some redshift of 0.9, so to make sure that we really have clusters in there. So I can't tell you which ones got cool cores or not, but probably not cool cores. And what I imagine is that you've got these jets, they don't make bubbles. Somehow they manage to create a little chimney that goes once through it. Once you've got this chimney going through the intercrystalline medium, then I think it's fine to keep pumping and without stirring the ambient medium too much. I'm more worried about the
But there's
ambient
no
medium.
mechanical feedback. There is no mechanical feedback out in the group.
At that point, that, well, yeah, but I mean, it has to be this fine balance that the black hole keeps being fed. So there must be accretion onto a steady accretion onto the black hole that somehow, without feedback, manages to stay steady. I don't know how that can possibly work.
Maybe it's a perception.
Well, yeah, so there's people who talk about the dentist drill effect that we can do in order to see, yeah. Right, so precession maybe could give you just this fine tuning of just heating it just enough to give you the right cooling rate to the bottom of the potential well, yeah. But nobody's ever simulated them. I've been talking to while I was here to Franco. Nobody simulated GOGs. It'd be interesting. I think this is now the next challenge, and this is a part of my mission now to get people to simulate it. Properly in the cosmological setting where you've got all the ambient motions in it, and yeah.
Just
One question. Emanuela.
Okay. Just thank you for your talk. Just a quick thing about the filaments, for example, the one in figure 194, for example. You talk about a sort of like, say, lack of X-ray emission corresponding to filaments. And would you say that there are more like tunnels that are filled by the, let's say, filaments themselves, or are the filaments that, thanks to like local acceleration of particles, can be able to push a little bit further the ICM, for example?
You saying which one was first, or I didn't
No, I mean,
answer that.
Can it happen at the same time, or I mean, can the acceleration of particles be responsible for the lack of X-ray emission localized with filaments?
I think the lack of X-ray emission is just the displacement of the thermal gas that's being by the pressure of the non-thermal particles. Now the question is, how do you accelerate the particle? Because the cosmic rays that produce this emission in here that live all along this flux tube, they are here, but the flux tube is 200 kiloparsecs. The radiative loss time you can work out because you know exactly how bright this is. You know this should really. I mean, the electrons that are here, they can't really come from here because by the time they reach this, they should have really faded. But where else should they come from? So they do probably come from here. And while they move along this tunnel, they somehow get pumped energy to it. But the energy pumping can't be very drastic because these are all, they're so laminar, so filamentary. So you can't have crazy turbulent motions in here that somehow keep them alive. So everything that goes and produces reacceleration mechanically has to be on scale smaller than what we see. But otherwise they would get disturbed and it would look like a wiggly line, but it looks like a straight line. So yeah, what happens? People have been looking at solar stuff and coronal mass, coronal loops in the sun and things like this to see, is there a way to do this? It's probably some fancy plasma physics that we don't understand. One question, somebody.
So a question about the low bending angle in your giant radio galaxies. Could this also be due at least partly to a selection effect, because you're only able to see those super giant radio galaxies out to 5 megaparsec distance only if the bending angle is very, very small and you're missing out all the others.
Yes, that could well be. It's a good point. I was worried about this. Yeah, we identify those because we see a lobe here, and then something in between. What if this middle thing has gone somewhere completely different and you wouldn't even associate it with that
I
galaxy
think
anymore?
if it interacts a lot with the ICM, it will lose surface brightness, so your capability of detecting this would be lower than.
That could also be the case. Yeah. So that's right. So that's a good point. That's a good point. And so that's why we also don't make strong claims about the bending angle statistics. I've shown you it's a bit of a funny distribution anyways. It's not clear that we don't see any statistically significant trends. Just there's all these kind of things in there. But still, what's enough already is to say that there are actually some that are so straight. So explain those. And there's probably more that are not straight. So yeah, which ones are we missing? That's another question.
Further questions? Simulation.